grade 12. So here's where we left off yesterday. Yesterday, we wrote a class called the tree class. The tree class uses our tree node class, and based on a root, an initial tree node, it will then be able to construct a tree. So the constructor is available to us, which just sets root to null. And we are able to insert data into our tree. And the way we do that is, if the root is null, then we just create a new tree node that holds the data. But if the root is not null, it uses a recursive insert method to insert data off of the root. So we looked at how that worked yesterday, and I hope that's clear. But where we left off yesterday was, how are we going to be able to go through a tree? Or the proper word I was going to say was traverse, to travel through a tree. Okay? So in the past, the way I've done this is when we go through the tree, I just output, I do like a system out, and I output the node value as we're each spot. But I think we can go a little bit better this year. So I'm going to suggest that to our tree class, we're going to add another property, a private linked list, because we already have that, of data type T, just called the list, okay? So we're going to have a list here that will be able to keep track of data if we need to. So so it'll allow us to turn our linked lists, or pardon me, turn our tree into a list if necessary. So it'll allow it to become linear, because it's not. So we're going to have to add that to our constructor. List equals a new linked list of data type T. Okay? Oops, extra bracket there. So that's now added to our constructor. That when we build a tree, we'll also build a linked list. Now, as you can see, the linked list won't take up any memory. That's one of the beauties of the linked list, until we need it, right? So it's not like an array where it's taking up memory unnecessarily. The beauty of the linked list that we've been building is it uses memory wisely, okay? Okay. Now, this will all factor into our toString method as well, which we'll get to. But before we write a traversal, what if we could search our tree? Okay? We did that with linked lists. But with trees, searching is different, right? Like let me show you a quick tree. Like what if I went 50, 40, 30, 45, 70, 60. Okay, so there's a tree. So imagine I was searching for 42, right? Or imagine I was searching for 40. What's the answer that comes back from that search? Like in a linked list, it was easy. We could say, well, it's at spot 5. But we're not really, this is not a linear structure, so we don't really need to keep track of sort of where it is. So the simplest search we could apply is true or false. Is 40 in the list? Yes or no? Is 42 in the list? Yes or no? So let's do that. Let's make a simple search that just returns a Boolean. Okay? So let's start with that before we do the traversal. Public Boolean search for T data. Okay? This is not a lot of code, because we're going to do it recursively. So we're going to return a recursive search for the data. Okay? Which means we're going to be creating a little private method called recursive search. What's that called? Who remembers? What's that called? It would be, the method would date Kim Kardashian. It's a wrapper method, that's right. It's a wrapper method, right? So it's a private Boolean, okay? But before I write it, I'm going to add a second parameter. We're going to search for the data starting at the root. So that's the key there, is the root is the second parameter, which is what we're hiding. We're hiding that from the outside. That's why we just search for the data. But inside, we're hiding the fact that we're starting at the root. So this is recursive Recursive search for T data and tree node. And I'm just not going to call it root, but current. So based on the current tree node, let's do a search. Okay? Okay, like I said, there's a lot of code here. But let's see how it works. Basically, if current equals null, what that means is I've reached an endpoint on my tree. So if I've reached an endpoint, I return false. There is no data of this type in this tree. If my current, so for example, if it was an empty tree, root would be null, right? And if current is null, it's not in there. This is an empty tree. So if current's null, return false. Else, if current, or pardon me, I take data, that's the parameter, dot compare to. Compare to is enforced because we use the comparable interface. We cast it as type T. We have to do that. Current dot data. Okay? And if that's less than 0, so that's a nasty line, but that's what it is. We compare the data to current's data. We have to perform a cast there because it doesn't know, that's just casting. And if it's less than 0, what that's basically saying is if it's less than this, then I return recursive search for the data and current dot left. This is a recursive call. So if it's less than, then go ahead and search the left subtree from this point forward. Search the left subtree. And then what I have for the next part is another else if. And if I use a greater than 0, I search the right subtree. And then finally I have an else. Let me just break this all into there. Can you guess what the else is? That's right, return true. The only other option is, there it is. Because if it's not less than the data, and it's not greater than the data, then it must be equal to the data. And if it's equal to the data, I return true. So if it's a null, it's not there. Otherwise, go ahead and search the left side, or go ahead and search the right side. And if it's not less than or greater than, then it must be equal to, and I return true. That's how I perform the recursive search. Simple code, but you have to understand recursion. Okay? You also kind of have to understand that this is not a linear structure, that this is a left-right structure in the binary tree. Now, we can kind of put this to the test, kind of. Even though we can't see the tree at this point, even though there's no way to output all these nodes, I can search. I can do a system out, and I can do tree.search for 30. Okay? It should return true. 30 should be in this tree because I inserted a 30. So let's see if my code works. True. So that's good. Okay? Let me test one of my other ones that's in the tree. Let me test 40. It was the last one I inserted. True. 40's in the tree. What about 50, the first node I inserted? True. Now let's try one that isn't in the tree. 100. False. Good. It works. And as a matter of fact, it is incredibly efficient search. You may not realize what's going on here, but what this search is the binary search. Okay? Now we haven't done the searching and sorting unit yet, but the binary search is the most efficient search there is. The only way that it works is because we're in a binary tree. Because we inserted the nodes already in order. So the nodes are already inserted in order, and that's as a result, this search is incredibly efficient. Okay? Way more efficient than a linked list. Way more. Okay? Like significantly more efficient. All right? So we now have the insert. We can insert nodes. We have a search method. What's left is the way to travel the tree. Okay? The way we're going to travel the tree. And the way it's going to work is it's going to be part of our toString method. Here's the way the toString method is going to work. We're going to take our list, okay? And if it's already got something in it, we're going to rebuild it by making a new linked list. So we'll just make sure it's a new linked list first, just in case we're calling toString for the second time, okay? And then we'll create a string called output, okay? And we'll put tree traversals on there, okay? And then a new line. At the end of this, we'll return output, okay? But what we're going to do is we're going to fill up our list, essentially, okay? And we'll say list equals, and we'll get the list from what's called the pre-order traversal, not pre-order traversal. So what's going to happen is this method that we haven't written yet will return a list of values, okay? We will then take that list and attach it to output. Okay, so output equals output, or plus equals the list.toString. We'll turn the linked list into a string and attach it to that. But we'll attach something else to it first. So before that, we'll also add that this is the pre-order. Okay, like that. And then we'll turn the list into a string. There are 3 traversals we're going to be looking at. One is the pre-order, so maybe we can even number them like this. 1, the pre-order. Okay. And then we're going to do this 2 more times. So after this, we'll do it again and again for post order and in order. Okay? So we will pick up on this tomorrow.